All right, guys, let's get started. Okay, so we're gonna get started. Today could be the last lecture on large language models before we move on to something else. So we've spent the first 4 or 5 weeks of the semester looking at machine learning problems and tensor operations, right? And we've seen every operation at this point. And so all I'm going to do now is put everything together to create that, GPT Huck Finn. So we'll go through the whole code. Remember, this is the code that you will use for the second assignment, and you guys are using the first assignment to collect your text data. Okay, does that make sense? So yeah, so this is pretty much should be very familiar. The whole point of the first few weeks was that every operation was familiar to you so that when we bring everything together, it's pretty easy. Okay, but it'll be a complete one, and this will have certain parts that we haven't covered before, like dealing with real data and also the optimization part, the training process. So I'm going to get started here, and I'll remind you exam one is next week, right? So a week from today will be your first exam, right? Any questions about the exam? Nope. All right. So let's yeah. So a week from today is exam one. All right. So let's take a look at you guys are section one, content, and essentially, so we've covered ML word problems, tensor operations, the Baby GPT, essentially, and you are reading these notes, right? You're reading through all the code, everything, and the Vaswani paper. So that's essentially where I will, yeah, so that's going to be exam one. All right. So exam one is going to be about here, which makes sense. That's pretty good. When the second third of the semester, we'll cover actually how to create very simple neural networks. So if anything, now we'll look at very basic operations, creating simple neural nets for regression, for classification, things like that, leading up to images, which will be about the third of the semester. Okay, CNNs and all that. All right. But yeah, so this is kind of so you have to study essentially from the beginning until about here for the exam. Okay. All right. So if you remember, the link is provided here. So we can go to the code. So let me close this. We can go to the code. And I've covered all these Jupyter notebooks now, and I'm just left with the GPT Scratch Huckleberry Finn. So now we're going to proceed to train. Now, remember, in this example, I don't use tick token, right? That's for you guys to figure out for the term project, right? So this is going to be even because I don't want to obscure anything, right? And tick token would obscure certain parts of what we're doing. So instead, we're just going to do the tick token part from scratch as well, okay? In a more fixed way. And so that's really the code that I'm going to cover. You're going to need a couple of things for this. You're going to need, of course, HuckFin, okay? The TXT. So we're going to need this file as you will be training from it. So what you can do is you can put it on your Google Drive. So I already did that. So you go to Google Drive, you press new, upload, and then it'll appear there. Does that make sense? So that's the approach. Now let's go ahead and I've loaded the file so we can go to Colab. And we're just going to start processing. Now, in theory, we should need a GPU for this, but it'll take me a while to go through all the code, right? So I'm going to just select the CPU first, and then probably during the second half of today, maybe we'll select a GPU and see some of the training of the model. Okay. So the runtime, if you remember, that's where you can select the GPU. Okay. We are going to mount the drive as I am going to need The Adventures of Huckleberry Finn. Drive. And there it is, Huck Finn, TXT. Okay. All right. And we'll just need the path to be able to connect to that. Let me see if I can find that path. The where copy path, just in case. All right. Okay. All right. So typing this up would take forever, right? So I do recommend that you guys at home type it up, develop some muscle memory when you're working with this, but I'll just bring it in from that notebook and kind of emphasize what we're doing. So we're going to need some libraries for this one. So I'm going to go ahead here and click on. So remember, now we are getting into GPT from scratch. Believe it or not, this is it. Chat GPT, right? You always thought, wow, Chat GPT, it's amazing. This is Chat GPT, right? No mystery, right? Code is available. You understand probably most of the operations, but you still can't do it, right? Because you don't have, all the data in the world and thousands and thousands of GPUs to be able to process efficiently. You can only process a few files, and you'll see that in this exercise. All right, so this is a GPT from scratch in PyTorch. So we're going to go ahead and import some of the functions. If you notice, some of these we have already looked at. So torch, right, to create our architectures, NumPy, torch NN. Today, we're going to start now creating architectures, right? More complex architectures of neural networks. And we're going to look at the instance of taking our object-oriented approach, our classes and everything, right? So everything that's going to be done, there's so much code involved, right? That really the only efficient way to code these neural networks is in using object-oriented programming, classes, and so on. So that's going to be a constant for the rest of the semester because that's really where the efficiencies come in. All right, so let's go ahead. And then torch NN functional would give us some of the functions, that we need. Okay. All right, so I'm gonna, look at all the parameters now, but although there's many, you should also feel somewhat comfortable with some of these. One of the things that's a little bit strange sometimes with PyTorch and these models is that you have to tell the data and the models explicitly to use the GPU. Some parts of this are being run on the CPU. All right, so a handy command that we use or statement is create a variable called device, and then basically we have an if statement. If torch CUDA is available, then we assign CUDA, else CPU. What is CUDA? CUDA is the CUDA library from NVIDIA, essentially the C code that allows you to use NVIDIA GPUs for machine learning. Okay, so that we want to make sure that that's available. And it will be available if you've installed it and you have the proper GPU. Now, keep in mind, now I'm going to be using the dimensions that we've discussing. Some of these dimensions are going to be the ones from the paper. So the block size and tokens in sequence. So what is block size? You can think of it as the length of the sentence in tokens, right? Okay, so that's essentially what it is. So 40 words, 40 syllables or subwords. In our case, 40 letters, right? Because we're going to do this from scratch with letters. But you can see 40 is that 32, 45, 12, right? So that parameter. Batch size, that's that 32, right? So I can change this to 64, 32. That's what it is. Max iterations is a parameter we haven't used yet, but we'll use it for training. So it's the number of times that we're going to do the training in a loop. we'll see that how that works in training. This is the first time we'll train something. Eval iterations, this is another step you can do. You've trained the model. You want to do a few iterations of evaluation just to see what the information tells you. The learning rate is another parameter that we're going to learn about. Requires quite a bit of going deep into things. For now, let's just think of it as like the update that you make, right? As we are learning, we know that neural networks have weights, right? We've said this many, many times. I've given you a lot of weight matrices that were random. But what happens is we need to update these weights, right? And we only do it incrementally. So this 0.003 is a step size, essentially. So it's like I have a 3, right? And I want to update it by adding to it. So I'm just going to add 0.003. Do you see that? And it just becomes a little bit bigger. And then the next time I want to update it, so I just add 0.003 again, and I update it. You see that in increments. It can also decrease. So we'll discuss that. But that's essentially how we update the weights of the model. Okay. And please stop me if you have any questions at any time. A lot of these terms we'll come back to later. Vocab size, you can see I've specified it as 88. Why 88? In the past, what was vocab size? I think we've used 1,000. We also mentioned 50,000 for the number of tokens. But in this case, it's 88 because I'm only using letters. So it's going to be like A through Z, that's 26 letters, lowercase, uppercase, a few numbers. You'll see that in a second. So it's about 88. And then embedding, you should know this, right? Very familiar. That's that 32, 40, 512. We've spoken at length about it. That's what 512 is. Now, this is a new parameter, attention heads. Do you remember what this is? Do you remember the process where we concatenated 8 things, right? And QKV, right? Those heads. So that's what this is. So we're just saying that we're going to use 8 heads. So here you want to make sure that we're going to be compressing from 512 to 64, right? So then you have to make sure that 64 times 8 gives you 512. If you were to change that dimension for some reason, you have to recompute the exact number of heads you need. Any questions there? So that's the concatenation part. And layer. So notice now that I have a 6. Before, if you remember, I only had 1, right? 1 block. So this is probably one where I should bring up the notes that you guys were reading. You can take a look here. This. So if you remember, there's 1, 2, 3, 4, 5, 6 blocks. Okay. So now we will have these 6 blocks, but it's so amazing and how elegant how this is solved. Takes a little bit of understanding, but it's amazing. So we just define 1 block and then in a very nice way, we bring these in. Okay. So that's essentially all the parameters. Dropout. It's something that we will talk about later, but it's one of those things that in the layers we use all the time, right? So dropout will make sense a little bit later. All right, so that ran fine. Now we're going to go ahead and I'm going to show you the code to bring in a book. So we have to specify where Huck Finn is, so I copy this. Okay. And it's going to be input file 2. All right, I'm going to comment this one out. Just like that, right? So input file content, The Adventures of Huckleberry Finn. I'm going to open that file, read it. It's UTF-8, which is the formatting in Gutenberg. And I'm just going to read it into this variable text. So let's run that. All right, we got a little green check mark there. So there you go. You just read a lot of text into RAM memory. Obviously, if you had all the books in the world, you can't do it at once. So in that case, you would have to develop some kind of a batched approach, right? So we keep talking about batches, right? So what do I mean by batches? We give it what? A batch of 32. So what does that mean? 32 samples, right? So 32 images at once or 32 sentences. Why was this developed? This is developed because you can't give it all the text or all the images, right? So you have to give it kind of like, analogy, like, you remember those old trains with the charcoal, right? And you're putting it in the engine and then more. So that's a batch, right? So that's kind of what we're doing. In this example, I'm just reading one file because it's very small, but if you have a lot of data, you would have to coordinate between the data in the file, in the hard drive, and what's going to go in memory. All right, so we've got our text file or our text variable. Now let's proceed, first of all, to inspect it, and then we're going to learn how this data needs to be fed into the neural network. This is a very important concept, okay? Ties a little bit into the attention score and the mask. We talked about that last week, correct? The mask and everything, the trill, all that. All right, so let's take a look here. Okay, so notice length of data in letter or characters. So I'm just taking the whole text variable as a string and I'm printing. So there's about 590,407 letters. This is a metric that I want you guys to quantify when you do your project, but you're using tick token, so it's not going to be letters, it's going to be subwords, okay? This is really important. Why is this important? Because it gives you an idea of the size of the data that you use. You see what I'm saying? So maybe someone used 590,000 tokens and then someone else used 10 million, right? Who do you think, might have a better model? Or someone used 1 billion tokens. Go ahead and read the literature on Llama 3.2 or GPT-4 and see how many tokens they use. So this is a nice way of quantifying, right? This is not unique tokens. This is just all tokens. All right. So we have that done. So pretty easy so far, right? These GPTs are pretty easy. All right. So we've done that. We know the number. Now let's take a look at the set. So the set just gives us like the unique characters in here. Okay, in text, and we can see these are the unique letters, numbers, etc. Right? That's what's in there in that story of the adventures of Huckleberry Finn. Okay, so we've done that. Now we're going to proceed to look at certain things. So I want, first of all, now I need to identify the vocabulary. So I'm going to use this. It's just some Python functions to create a list from I'm going to take the text and I'm going to create a set. This is going to give me all the unique characters, okay? And then those characters are going to be placed in a list, sorted, and that gives me the actual characters that will make up my vocabulary. All right, so there they are. So this is going to be your vocabulary. These things need to be converted from numbers to letters and vice versa. Okay. Oops. I'm going to close this one. All right. So now we need the size of the vocabulary. I think it was 88. But vocab size is the length of the chars. So, or maybe it's 65. No, it's 88. All right. So that's the size. Pretty important, right? As a parameter. And that's the thing that we need to take as input, convert to integers, and then the model needs to learn to predict. Okay. If we want to look at the information, we can just print it out. All right, so the chars, the length of it, and then just look at it as a string for convenience. There you have it. You can take a look. So these are the special characters. All right. So all of that was pretty easy. Now we're going to create tick token, essentially. Tick token was just a, if you remember, we would give it strings and it would give us integers. We would give it integers, it would give us back the strings. Here we're just going to create our own with a dictionary, a couple of dictionaries. We do this is common practice in natural language processing. These are called forward and reverse dictionaries. So essentially it's the same dictionary, but where you've inverted the numbers and the letters. So you have number letter or letter number. It's just easier to do a search, when depending on where we are. So you can see all we do is we have a for loop. So for I, comma, char ch and enumerate the char. So we just iterate through them. This way we'll get a number and the actual character. Okay. And that way we create, if you notice here, a pair of character and integer. And then we repeat the same process, but reverse this to be integer and character. Essentially two dictionaries and just in reverse. Okay, so we'll see that. Should be able to see that in a second. Okay, so if I print both of these, you can see here, for instance, that let's say I'm looking for like the letter C, right? So I'm looking for C, so that's 28. Do you guys see that? But if I have down here, if I have 30, then it tells me that that's an E. Do you see that? So it's just a quick way. I have integers, I get letters. If I have letters, I get back integers. Any questions on this one? This is your tick token from scratch. Okay, pretty simple. All right, we've completed that part. Now let's just do some examples or experiments. So here I'm going to, this is a lambda function. Okay, given S, it applies whatever's in here. So in here, all I'm doing is a list comprehension. So S is the string that I give it, like bat, right? So, or something like that. So force, and then it's going to iterate through it. So for C and S, and then it's going to look up what C is in this dictionary, string to integer. And it's just going to return the integer. So here I'm going to give it bat to encode. And there you go. Got my integers. Do you guys understand? That's it. That's from scratch. Tick token. Obviously, tick token provides, a better, like the most frequent set of characters, pretty good in that regard. But here, for simplicity, we're using this approach. When you do your assignment, you should try this and also tick token, and you will probably be surprised that there's a high improvement when using tick token. So that's a really key feature. All right, let's go ahead and try another one. So this one is the same thing, another lambda function, but this creates a string. It just iterates through a list of integers, and it runs them through the dictionary integer to string, itos, and that's it. So here I have the list 55, 54, 61, 61, and I run it, and it gives me back bat. Okay. So that's it. You've created your own little tick token. And this will definitely give you words and things like that. It's not the best approach. All right, so now let's go ahead and get more real. Oh yeah, please go ahead. They were not the same? 55, 54, 61, 61. 55, 54, 61, 61. From this? Well, I'm using that dictionary to convert between integers and letters or letters into integers. No? So that shouldn't 55. All right, let's do B, right? Letter B. Help me find the letter B. Well, it should be 55. It's what? Oh, yeah, it is cases. Oh, yeah, it is case sensitive. It is case sensitive. So that's what probably, yeah. So there's uppercase B and lowercase b. Yeah, I should have. You saw it before. I see. Okay, I understand that. So you saw it, uh, this one, right? And it didn't match. Yeah, good catch. So it's using, like ASCII characters. So it's going to be uppercase and lowercase. Yeah, very good. I mean, we are using that function, so there's like no way it couldn't work. Right, sorry. Let me just kind of charge my. All right, great. So should be doing good. So any other questions about the dictionary, guys? Nope. All right. So we did back and forth, right? We went from bad to numbers and then numbers to bad. So that's good. Now, uh, I'm going to do this. Yeah, I was doing this part. So I didn't paste it, I think. Yeah, there we go. So now notice that I'm going to take the entire text. So this is equivalent to taking the entire Adventures of Huckleberry Finn. I'm going to encode it, right? Every letter into an integer, right? And then I'm going to take that and convert that into a torch tensor. Why does it need to be a torch tensor? Because we're going to be building a neural network in PyTorch. And PyTorch in the computational graph does not take anything other than torch tensors, right? So we have to convert everything. All right, so that's this one here. And there we are. So that's the entire book converted now to integer. Do you guys see that? Pretty amazing, right? So now we have our data to use. Okay, we have our data. All right, the next step is to split the data into train and test. This is just good practice, always having a little data set outside to be used for something, okay? So in this case, I'm going to do data, the actual tensor now. I'm going to split it, just take the length of it, and I'm going to just say 90%, right? So that gives me like from 0 to 90%, 90% to the end. And I'll know the index where the cutoff happens. All right, so I can slice this. So if you notice, what I'm going to do is from the beginning, now you guys should know how to do this really well, because at this point, you're probably on your 7th pass of the 110 tensor operations, right? 8th pass, maybe, right? So that was in there, right? So those are the tensor operations. So we go from beginning to end, okay? Which is probably a very high number. And that's going to be the train set. So essentially, like if the book has 10 chapters, right? Maybe the first 8 chapters are for training. The last 2 chapters are for testing, okay? And then, so I have train data and validation data here. And now we have our training data. Do you guys see that? So a set of data that we can use to train the GPT. All right, now this part, now comes the hard part. So I have this function. This is the function that we will use. I have actually broken this into parts that I'm going to go through, okay, individually. But essentially, this will be the function that we will be using, get batch, to get our data. This is the part that gets a little bit different from machine learning, right? That we have to figure out. So let me switch to the whiteboard for a second here. Okay, perfect. So as we will see in the second third of the class, we'll start classifying like regression things, like just predicting the temperature. I think, we'll do something very basic like that, predicting temperature. So if my temperature is from Celsius to Fahrenheit, right? So if my temperature in Celsius is 0, then what's my Fahrenheit? It's going to be like 32, correct? But we're going to train a model, right? And the model is going to learn to correlate. So imagine this is a model. It's going to learn to correlate these two. So I'm going to have this notion of X and Y. Do you guys agree? X and Y? We talked a little bit about this in the word problems, correct? So in the next few weeks, we'll do like a temperature one. Then we'll do probably iris, right? What is iris? It'll have 4 inputs, go into the model, and it'll do a classification of Setosa, Virginica, versicolor. Do you guys agree? We'll do something like this. So pretty straightforward. We'll have an image maybe of a cat, and we'll just say it's a cat or a dog, right? So here, what's important is we have this notion of X and Y, X and Y, right, on the other side of the model. The thing that goes in, and then what it predicts. The model predicts, and we're going to compare it to this thing to minimize an error. That's going to be the overall logic. But in a GPT, the question is, what is X and Y? Do you guys see that? That's really like the critical thing. What is X and Y? So we know we have this notion of text. So what we're going to learn is, in fact, that just when we're looking at a batch of 1, and this might amaze you, the same sentence that goes in comes out with one slight modification. So that's the first. So initially, don't even think about the modification. Just think of the same sentence goes in and out. That might be like very easy to think, right? So you might say like, you'll say like, the cat is sleeping. Guys in the back. The cat is sleeping, right? That's the input. So and the output I'm saying will be the cat is sleeping. But that can't be it, right? So there's one more thing. So the sentences are the same, but they have to be shifted by 1. They're shifted by 1. That's the only thing that you need to understand. So for instance, this is and imagine that's that whole, those blocks, everything, attention layers, etc. But what goes in and what comes out in a GPT is the same sentence, but shifted by 1. So what do I mean by that? So the cat is sleeping, right? And then over here, the cat is sleeping. So where does the shift come in? You guys see that? That's the shifting. Because we're trying to learn how to predict the next word for every input. Does that make sense? So now that you've seen this, let's rearrange this a little bit better. We can't look ahead, right? That would be cheating. Remember that whole discussion we had, right? And so really, I'm going to write it a little bit better here by saying something like, the cat is. And then over here, I'm going to say, cat is sleeping. So remember that these have perfect dimensions, right? These are tensors that have absolutely perfect dimensions. And so these things need to almost align. So it's like you can imagine there's like an imaginary flow like that. Whoops. Do you see that? And then there's a flow like that. And then there's a flow like that. So, yeah, I give it the, and it predicts cat. Do you see that? I give it cat, and it predicts is. I give it is, and it predicts sleeping. And this, by the way, is the word that it hasn't, that we're looking for usually, because, we're going to give it complete chunks, right? You're going to give it this whole sentence, and it's going to predict learn to predict like this. But what matters to us is that we're trying to guess what that word is. Do you guys see that? That's essentially what it is. Now, there's a difference between how, and this will take you a bit to grasp. There's a difference between how we train and how we run the inference or test it. During training, we do a slight different thing. Same architecture, but just a little bit different. And so the thing that you should make a note of is that we use an idea called teacher forcing, all right, during training. And that will give you some insight into the difference, all right? We'll talk about that later. But that's essentially what is happening. So whenever I feed data to train my GPT, let's not even worry about inference right now, just to train, I'm going to grab a chunk of length 40, right, or something, a sentence. Once I have my sentence, I shift it by 1, and boom, I have my X and my Y. My X goes in, it'll predict. Remember, you should believe, right, that it's going to here predict bird, blue, green. Is that a good prediction? No, right? No, because what you wanted was, see, this is what the prediction, this is the input, and this is the prediction. So let's denote this as X, Y, and Y hat. Do you guys agree? So we have X, the input, Y hat, and Y. And so what's going to happen is that think of the neural network as just a function, right? So X goes in, and it's going to predict Y hat. But you also had Y, right? Because that's your training data. So what do? You're going to find ways to minimize in some type of an error. And you want to, that's your objective, to minimize that error. And then once you've minimized that error, you're going to use that information in what is called backpropagation to update the weight. So we will see that in, definitely today we'll implement some of this, and throughout the semester we'll dig deep into these concepts, okay? But that's quite simple, right? So it's like amazing that this works. Don't even like worry about why it works, but it does work. So essentially then, we need to give the input as the cat is and cat is sleeping, where the word that actually, whenever you ask it a question, it'll regurgitate basically the question you just asked it. But what you care about is that next word. And then what do you do when you have that? Now that's now in inference, what do you do with that new word that you just got? Well, you add it to this one and you bump this one out. So now the new input will be what? Cat is sleeping. That goes in. What comes out here? So cat is sleeping goes on the table. So this comes out as is sleeping on. And then that on goes down here and so on. Do you guys see that? So that's essentially, these are called autoregressive models, and that's essentially one of the key features. Okay? All right, so now let's see this in the code. And, that function seems pretty hard to understand, but it's actually somewhat easy, I would say. We just have to break it down. What I always recommend, right? Break everything down into the simple tensor operations, print out the shapes, and boom, you're good. All right, so this is the function. I'll go over it first, and then I'll break it down. This is what we will use, get a batch. When we're training, we want a batch. And how do we get the data? Well, you could devise a whole plan for it, but we're training a large language model. Assume that you have infinite GPUs and infinite books and internet, right? So infinite sentences. So do you have to have a structure? How do you even structure? Okay, do I start with Wall Street Journal? Do I start with news? Do I start with math? What do I start with, right? Comics? A novel? It's really hard to say, right? So it might be better just to start randomly. So you just have this whole data set and you just randomly get me a sentence. Better yet, get me a batch of 64 sentences. Then all random. Then get me another batch of 64. Do you see what I'm saying? Once I have these 64 sentences or one, what do? I just grab one input, then make that the input. And what do we do with the output? We just shift it by one. And boom, we're there. And then we train. That's the trick, okay? So let's take a look here. So we're going to say, essentially, if we're training, that we want to use the train data, or otherwise we'll use the validation data. But essentially, we're grabbing either the first 10 chapters of Huck Finn or the last 2 chapters of Huck Finn. Got it? Then over here, this statement quite simply just gives me a list of random starting positions in the book. So it's going to say, okay, grab sentence 17. So you look at sentence 17 and grab that one. That's the starting point. You can just, the length is going to be the block size, or the length of the sequence. Do you see that? Then I grab another integer, 53. Okay, that's sentence 53. Boom, I grabbed it. And then we just shifted by one. So now notice that's this part here. Look at how elegant this is. So there you have your X and Y. Torch stack, we already talked about torch stack. It's in the 107 problems. Notice from data, all we do is we're going to create a list, right, of chunks, a list of chunks. But what we care about is we care about where to start in the text, right? We have a book and we want sentence 16. That's what this list IX contains. So we grab 16. Then we just slice from data from 16 to 16 plus block size. What is block size? 40. So from 16 to 56, we grab that chunk of sentence. So actually, we don't even need to grab a whole sentence. It doesn't matter, as long as they are sequential. That's really all that matters. Do you guys see that? Any questions on that idea? All right, and we do this at the integer level because we've already encoded our data. Remember, we are no longer dealing with letters, we're dealing with tokens. So if you remember, we've already converted the whole book data into just these integers given the dictionaries that I created for my vocabulary. All right, and then once X and Y are created, we just assign them to the device. So this is just so that it'll run faster. That means we're assigning them to the GPU. Sometimes you'll have errors if this is not done correctly, or it'll run more slowly. Okay, that's it. But even if you understood, let's view it. Let's visualize it, right? Now, of course, we need this function because this will be our training function, get batch. Okay, so now Let's go over here. And notice I'm going to create an example. This is outside of the GPT code. So when you do your project, you don't need this part. This is just a little example I'm doing. Notice I'm going to assume a batch of 4. So instead of 32, it's 4. So 4 sentences. And the block size won't be 40, it'll be 16. Right? So I can grab a whole sequence. So notice I'm going to use torch rand to create randint to create the indices from the beginning until the end of the data minus block size, right? So because if I need to have a starting position and then grab a whole block of it. So I can't be at the end, for instance. Okay? So look at what I do here. So notice I have my list. I have 4, right? Because there are 4 sentences that I want, batch size of 4. So what does this mean? It means if the text it was actually from 1 to 500,000, right? So in order, so get to position 47,000, and from there, you're going to grab 16 out, that whole sequence. Okay, let me show you in the whiteboard. We're going to go to the whiteboard. Okay. And what I mean is, I have the book, The Adventures of Huckleberry Finn, all that. And then one of those indices was like 1700. Okay. So this is 0. So you 1700, there we go. That's 1700, let's say. Do you guys understand? And then from here, you just grab a chunk of size, in this case 16, but it would be 40. So that this ends up being just some phrase inside the text. And that's it. Once I grab that, imagine that this says, Tom was on the raft, something like that. So that's what it grabbed. It could be Tom was on the raft and it just cut off because that's 16. It doesn't matter. Later on, if we do this enough times, we'll come here to 1703, right, and grab the rest of it. That's the idea. Okay, so now that I have this becomes X, and so Y would just be this thing but shifted, right? So it would be was on the raft and that's Y, and X would be without the top. No, wait. No, sorry. Come on, you guys can correct me, right? What would it be? Well, it would be Tom, but I have to get rid of the last one, right? Yeah. Very good. Exactly. Do you guys see that? Do you agree? Oh, did I do that right? Yeah. So, yeah. How simple is that? This is one of my favorite things about GPTs. When I first was trying to learn these things, I was like, how is that done? Like I couldn't. And then it's just that. It's like so incredibly simple and elegant. But anyway, so I really I think it's one of the great things of it. All right, so let's go back. All right, so notice I have my integers here, right? I have my integers. Now I can go over here and I can just see in the text what these integers are. And I think a lot of them are kind of the same. So notice I'm just iterating through these 4 and I look them up essentially in the data itself. I could just look them up and you can see it gives me that at that position, there's a 1, probably one of the first letters, there's a 59 and so on. Okay. So that part is done. Now notice this part here. And let's see if you guys can tell me what it means. Oh, I think I missed something. So in that same get block function, notice that now I have X and Y, right? And what do? I iterate through these four indices, and I'm just, for X, it's just I to I plus block size. Whereas in Y, it is I plus 1 to I plus 1 plus block size. That's the shifting. Okay? So that's the shifting that happens there. And you can see that there. So now I had four IDs, right? That's the starting position. And at that position, these are the indices that I grab. Do you guys see that? So the first one is X, right? So this is X, a tensor, and this is Y, the other tensor. So the way that this works is that this sentence and this sentence go together. That's the X and the Y for that index 1 in that batch. Now for the third one then, what does that mean? It means that this one goes with this one. Do you guys see that? And you should convince yourself of this, right? Well, look at the numbers. 1, 45, 61. Do you see that? Notice down here, 45, 61, but the 1 is gone. Popped off. Then over here, I have 82, 65, 65. Down here, I have 82, 65, 65, and then there's this 1 that wasn't there before. They have the same size, right? They're both 40 or 16 or 16, but they've been shifted by 1. And that's essentially the trick. That's like the key insight of a GPT. What do you guys think? Any questions? Making sense? Yeah. So, all right. So hopefully that makes sense, right? So this is our, this was before our batch of 32 by 40, right? So here's a batch of 4 by 16. But now we have an X and a Y. And notice that, I always said, right? 32, 45, 12 goes in. 32, 45, 12 comes out, right? So in this case, it would be 4, comma 16 goes in, 4, comma 16 comes out at this stage of the process. All right, so the next thing is, so we've done that. This function, we estimate loss, we can look at later because it's kind of like misplaced, but it's a function related to the training. So we'll look at it later. And that's essentially it, guys. Okay, that's essentially it. So I just did all these steps, but really we're going to be using this function, okay, for our training and our testing. Perfect. So now guess what? We are ready for the architecture to put together the entire neural network. So I'll kind of go over it, okay, of how this works. So notice I have these are the NN architectures. So that's like where the attention is, the feed forward layers, and all of that, okay? So if you remember the Baby GPT, right? All of that. So here we have the head. This is, like I said, from now on, we will be coding all of our neural networks in this approach, okay? So we'll learn this basic structure in a minute, but this is how we're going to proceed. A class, so you guys, should understand a little bit of object-oriented programming, right? You define a class, and there you can have variables and functions and things like that associated with that. So this class head has to do with what? With the attention mechanism. So this is that whole attention thing that we talked about is the head. If you notice, there's common things in there like key values already. There's key query values. What was this? What is that? Yeah, the attention scores, right? So the K matrix multiplication Q that gave you the attention scores, a matrix that was 40 by 40 or something like that. Okay. And, the softmax, we talked about the softmax in the context of the mask, remember? So that's essentially the attention head. Then we have a feed forward head, which we've talked about also. That's where we went from 512 to 2048, then from 2048 back to 512. That's what that is. This multi-head, if you notice over here, it's got the torch cat. So that's the concatenate part that we've talked about before. And then this is a block so that we can create blocks of 6. So that's each one of these decoder layers is going to be a block. And so we'll get to this in a second. But finally, this should look familiar to you because this has got that whole Baby GPT layout that we talked about before. So I'll start with this here today. And then we're just going to complete. And believe it or not, that's it. After that, I just instantiate the model. This here is now the training and the optimization. So just training them. Do you guys see that? So yeah. So not too bad, right? Not too bad. And so let's go ahead and you can see this will be the training. We'll talk about minimizing losses. And then after this, if you notice, it's just generating text. So we're using it to generate text. We can even use it to ask questions. So for instance, I have, where is Huck? That's a question. Like you ask ChatGPT, hey, explain this or that. What is Huck? Right? And then the model starts to answer the question. Got it? All right. So the place to start in this sequence is here, the actual class. Okay. So here's a concept now that it's going to apply all semester, whether we're doing something very simple or very complex. How to define these ideas of neural networks, these architectures in the code. So we're going to use object-oriented programming to create all of our architectures. Let's say that you're trying to build a simple neural net, right? A very super simple net for Iris, or you're building a GPT. Regardless, right? We're going to always use to define our architectures this approach. So we're going to create a class and we're going to give it a name such as GPT. And then it's going to be like this. It's going to take a parameter, which is like the NN parameter from Torch, from PyTorch. Okay. And then inside, it'll have 2 functions at least, always. It's going to have the init function and it's going to have the forward function. So this is sometimes called a constructor in object-oriented programming. So what's going to be in this init? All the declarations, okay? Like variables, vars, declarations, etc. And the forward is where we actually have the architecture. Okay, so we're going to define, okay, X goes in and we get Y. Does this make sense, guys? This is really important, okay? All of our definitions are going to be object-oriented like this, a class. There's going to be an init. It's going to be an init and a forward. The GPT actually has a third function called generate. We'll see that a little later, but these two are always going to be there. If we're building Iris, init and forward. And we're going to create a class called Iris MLP or something like that. Do you get it? Do you get it? So that's the idea. Okay, so that's what I'm going to do now. I'm going to go in to the GPT model itself. Okay, so I'm going to grab this class. Copy. I'm going to define it somewhere down here. And this should be very much like the Baby GPT, just now it has a lot of things. So notice here, there's the class, it's called GPT, and we inherit this thing called nn.module. So this is a concept also from object-oriented programming. You probably heard about it, inheritance. So essentially you created a class, but it would inherit a lot of properties from another class. And so that allowed you to like reuse things inside. Do you guys see that? So essentially it's always going to have this in PyTorch. All right, so if you notice now, let's isolate the functions, right? So we have the init function here. You see that? That's the init function, def init. These are two underscores, self. And then I've got here the other function, forward. And this is how PyTorch likes to use things. So that's this one over here, forward. There is a third one called generate, but I'm going to ignore that for now. In fact, I'm going to delete it for now. Okay? And we'll come back to it later. Let's just focus on these two. Generate is all, it's mostly for the inference part, not for training. Okay? So now let's take a look at what's going on here. So a lot of these models, because they inherit things, they always do this statement. Just assume it's always there. It's initializing the inherited class NN architecture. Even if this sounds complicated right now, you will learn to love the fact that you can inherit this NN module because it just makes this so much easier, okay? To be able to just use all the elements from it. All right, so now that we established that this is there all the time, let's take a look at what we have in here. So this should be familiar because we've already done it, right? What are these? These are the embeddings. Do you remember that we talked about semantic token embedding, and we also talked about positional embeddings? Do you remember that? So we've talked about this concept at length already, and that's what's happening here. Our X is going to come in, and it's going to come in as n by 40, and through this becomes n by 40 by 512. You remember that, right? We covered it in the previous videos. And then the positional encoding we've also discussed. So that's what's happening here. Notice that positional encoding is block size because it's 40 positions to 512. And vocab size is 88 to 512. I wrote 65 here, but it's 88. Just like that. Do you see that? And so now I haven't used them, right? I've only like declared them for me to use. The forward is where you actually use them. And the init is where you initialize. And this is just standard practice. I love this approach. And I think it makes your code just so much more organized, clearer, cleaner, easier to like fix problems, etc. It's definitely the way to go. All right. So that's done. That's amazing. Then if you remember, what we would have in here in the Baby GPT was just the code for one block. But the problem is we have 6 blocks instead of just one block. So this is probably like one of the biggest tricks that's happening here. So there's 2 ways of creating a neural network. There's 2 ways of creating neural nets. So I'll show you that in the whiteboard. And again, we'll see this later on. We'll practice it a lot. But I'm introducing right now, there's 2 approaches. When we use CNN, we'll use this NN sequential because it just makes sense to use it because for very like verbose, for things that have a lot of code, NN sequential is better. For things that have less, we can use the other approach, which is kind of my favorite, but there are situations where you just can't use it. So one way of declaring our neural nets is going to be something like this. So we're going to have like, we're going to have an X, that goes into linear 1, and that produces x. And then this x goes into linear 2 and produces x again. And then finally, there might be a linear 3, and this x goes in here. Remember, it's like this. Let me do this. Do you see that? And then we have a final y. So you see how the data is kind of like flowing. It goes in, it goes into this, then this goes into here, then goes into this, and so on, right? You're seeing that happening. With NN sequential, it's almost like you can do this. So the code for NN sequential is, oops, not here. It is NN sequential. So how do I get back to the how do I get back to the let me try it like this. Okay, so this is one approach, small architecture, minimal, that one. Complicated, like GPT, CNN, right? Then we want to use NN sequential. So in NN sequential, it's almost like we can just do this. Linear 1. Linear 2. Linear 3. Do you guys see the difference? So essentially here we have to explicitly say that this x goes in and then it moves down here and so on. With NN sequential, we don't, but the assumption is that my x data will flow through all three. So this can be very convenient when you, for instance, don't know how many of these you're going to do. Like in the LLM, we have 6 of them, right? So we have 6 of them. So instead of doing that, we just create a list, for I in 6 block. Do you see that, guys? So each block of each one of these blocks, you can assume that it simply has a linear layer in there. So essentially then this list becomes block, block, dot, 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 block. And then this block is what goes in there. And so now the data, you can assume that the X will flow through them like this flows through that. Do you guys see that? Is that clear? Any questions on that? This is probably like the most complicated part of this whole code, right? If you understand the old, because this is new, right? And this is more of a trick. This is like a coding expert trick, right? These people at Google and invented the GPT, they came up with these like amazing moves. But it just makes it very easy then. So usually a lot of the time we'll code like this, but when it's like a lot of lines and everything, GPTs or CNN, Stable Diffusion, will take the NN sequential route. Okay? All right, so let's take a look now back at the code so that we can see that part. So again, we're in init still. I'm defining the embeddings. I'm also defining self.blocks, which is going to be an NN sequential made up of just a list, and it's the list I just drew, right? So 4 in n layer. How many layers do we have? 6. So then, guess what I do? I instantiate 6 of these, which is 6 blocks. I need to define block, but for now, just assume it's an NN layer. for now. W equals, no, sorry, y equal wx plus b. And in linear that we've talked about, just assume that. And we have to drill down, but really what we have there is a sequence of 6 blocks. So if I go back to this, I literally, with that one line of code, just did all of this. Think about that. Like I just created that whole block of code with just that one line. 1, 2, 3, 4, 5, 6. Exactly. I know. We're all astonished by this. Anyway, but it's pretty impressive, I think. All right, so we've created this NN sequential, right? We have the 6 blocks, and we know that oops, sorry, was it a curly bracket? Yeah. Did I delete? Oh, this is probably okay. All right, so we know that any x that goes into NN blocks will go through all 6 layers. We still need to define blocks, so we'll do that in a minute. After that, we got this layer normalization, which is a normalization layer that it's something that we'll define later. But it's not part of the architecture. It's just to like normalize the values. And then I have finally, this should be familiar to you, right? Do you guys remember this? This is the last layer, NN linear, that goes from 512 to vocab size, which in this case is 65. So if you remember in the Baby GPT, this was the last part. Yeah, vocab size is 88. You're right. But yeah. So that's essentially all of it. So we've instantiated all of these. Now we can proceed to actually, in forward, we create the architecture. Okay? So we'll create the architecture in forward. So it's 6:18, right? So we started at 5. Let's take a 10-minute break right now at 6:18, and we'll come back at 6:28, and we'll look at this because this is really like the core that brings everything together, but also it's the Baby GPT that we discussed last week. All right, so let's take a 10-minute break, and we'll come back at 6:28.